Hi, I'm Jim. Welcome to part 2 of filters, and today we're going to be discussing active filters. And what that simply means is that there's going to be a DC power source that are feeding the filter. I've not shown the DC terminal pins on the operational amplifier. Make things simple. And there are several types of active filters, and the one we're going to be discussing is referred to as the Sallen Key, which was discovered in 1954 by a couple of scientists. And the general layout is shown here, and do note that these are impedances. So we can have the flexibility to substitute R's and C's into this to give us different filter operations. For example, low pass, high pass, or band pass. So by keeping things general like this, we're going to end up with a universal equation, which will be very helpful if we want to expand and do something different with a filter other than low pass. So to analyze this, we're going to start out with Kirchhoff's current law, and in this case I1 equals I2 plus I3, and I'm going to need a voltage here at this node that I've labeled V sub x, and that's ultimately going to produce a bit of a problem because we have three unknowns, V out, V in, and V sub x, and basically kind of one equation, but we'll take care of the V out and the V in by establishing a ratio which represents the transfer function. So the input current is going to be equal to V in minus Vx. That would produce a plus minus drop across the impedance, and this has to be equal by KCL to I2 and I3. And since the current is flowing in this way, this will be Vx minus V out divided by Z3. That'd be our guy right here. And then lastly we have I3, which is going to be Vx minus V out, this point, divided by Z2. Now, what's the deal with V out here? Certainly a good question. This is a unity gain feedback buffer, basically. And what we know is, as long as this is operating in the linear region, which it had better for filters, is we have a virtual short between the two inputs here. So V out basically is the same voltage as the voltage on the non-inverting input. So we can use V out as a label for this point since the voltage is the same. Now you have to be comfortable with an operational amplifier's configuration to be able to know that that's going to be V out. So that's going to be our current flow here for our third current I3 is Vx minus V out divided by impedance 2, which is this guy. And what we desire to do is get this in a ratio for the transfer function, which is V out divided by V in. So what our next mission will be is to try to get Vx in terms of V out and V in, and therefore we can substitute something in to make this equation a whole lot simpler and realistically solvable. So what I have is a relationship here, and we've seen before, Vx minus V out over Z2, and this is also equal to Z out, same point, divided by Z4. Current flows in this direction. Remember that the input Z of the op-amp is super high, and it's not at all a stretch of the imagination to make the assumption that it is not loading the circuit. So we have this arrangement for this, and all we need to do now is solve for Vx. So Vx minus V out divided by, or is equal to Z2 V out over Z4. So what I did is multiply both sides by Z2. Then, see what I did here, move V out to the other side by adding V out. So now we have Vx all by itself. And then kind of simplifying things up a little bit here, we have Vx equals V out times the quantity, Z2 over Z4 plus 1. So factoring out V out here is going to buy us a little bit of simplicity down the way. Now the math for this is detailed in the handout, and I'm not going to go through it. 3 or 4 pages to do that. And repeating the equations here, this is what we started with, and this was our Vx substitution, and this is going to lead us to the equation with the substitution. And you can see wherever we have a Vx in the equation is we've substituted in this value here, and now we basically have two unknowns. And what we want to do is get this V out over V in terms of Z1 through Z4, and then we can worry about populating those with actual physical values. So the transfer function in the time domain equals V out over Vn, and this equation here is what results from manipulating this into this form. Now, I had a bit of difficulty doing this. Tried maybe 6 or 7 times and always ended up with the wrong answer, and miswrote down the subscripts, and plus I was tired some of the times I tried to do it. So what I did is I just let Z1 equal A, Z2 equal B, Z3 equal C, and Z4 equal D. Wrote it out, had it solved in 10 to 15 minutes without error. So when you're dealing with complicated subscripts and everything is the same letter, you might consider simplifying in that manner, and then when you get the solution, just substitute in the subscripted variable and all is good. Further, if you have a situation like this, suppose Z3 times the quantity Z1 plus Z2 appeared many times in an equation you're trying to solve, and when you're solving this, instead of writing this term over and over again, is to let it be equal to X, and then when you get it down to the final solution here, substitute back in your terms. And you can do that as long as you don't have to pull a term out of here to do a simplification somewhere. So that substituting in simple terms can be very, very helpful. Continuing, a standard second order equation is this guy, and this is exactly the same as what we had in the passive second order equation in part 1. And then this is going to be our circuit, which we're going to see again on the next page. Just feel the need to draw it there. So, as before, so we can kind of do some comparisons, we're going to let our critical frequency, F sub O equal 15 kilohertz, and what this would look like on a Bode plot, depending upon the Q of the circuit, would be something like this, and the corner of the Bode would be negative 3 dB. And the roll-off now, since we're dealing with 2 energy storage parts, would be negative 40 dB. And circuit configuration looks like this, and let's pretend for a minute that I took C1, instead of connecting him to C out, I took him to ground. Now, that would just simply be 2 cascaded RC filters, and it would have a very, very lazy rounded roll-off and ultimately reach negative 40 dB per decade. However, if we connect it to the output, what we do is, it's called bootstrapping, is we're going to feed some positive feedback into this guy, and what we can do with that, very important, is to control the Q, the flatness of the response, the phase of the response. And in some applications, phase is very important. So this feedback path makes this a very, very flexible filter. Now, a common strategy when you're dealing with Allen key is to let the resistor values and the capacitor values be equal. So that's what we're going to do, and that's going to give us a standard Q, which is going to be very good, but we'll figure out how to modify it in a little minute once we get that far. So what we want to know is the critical frequency, and to do that, it's the absolute value of X equals R, and then solving for R, what we get is 2 pi FR, FCR equals 1, and then solving for R, and our critical frequency F sub O equals 1 over 2 pi RC, which we've seen before. Now, we're dealing a lot with omega, so what I want to do here is divide both sides by 2 pi, which will give me 2 pi F sub 0 equals 1 over RC. And it's important that you're comfortable with omega 0, because lots of the stuff uses omega instead of 2 pi F. So in doing that, as you can see, omega 0 equals 1 over RC, and then I'm going to be needing an omega 0 squared term. So that's just equal to 1 over r squared c squared, and that breaks down into r1 r2 times c1 or c2. Now the product of these two, r1 and r2, is going to be equal to r times r, and the product of c1 and c2 is going to be equal to c times c. And that can be seen from up here, but a little bit later, when we change the values of c1 and c2, the product has to be equal to c, or what we'll do is change the corner frequency. So I can also say that omega 0 squared is equal to the term we just had here, and that would be equal to this term here, which I've kind of written down again a second time. And what I want to try to do is get set up to do some substitutions. So if omega squared is this term, then omega has got to be 1 over the square root of this term. So on this page I've kind of got a lot of things that I'm going to be needing to solve this, and Q is equal to omega 0, well, the B term is equal to omega 0 over Q, and then by doing some substitution up here, and this is all in the documentation, again a lot to write, we end up with this term, and this simplifies into Q equals 0.5 times the square root of C1 over C2. Now note that C1 is this guy, so as the ratio of C1 and to C2 increases, the Q goes up. Okay. So to find actual values to put in a circuit, what we're going to do is choose C and then see if R is a reasonable value. Now we don't want the values to be too low where the op amps can't drive it, and we don't want the values to be too high where they're subject to ingress and interference from electrostatic or electromagnetic fields. So I start out by letting C equals 10 nanofarads and then solve for R by this equation here, and R comes out to be 1061 ohms, fairly reasonable value. Now when you deal with finding frequencies like this, it's unlikely that you're going to end up with clean numbers. So fact of life. So this is called an equal value filter, and solving this for Q equals 0.5, and this is called a critical frequency. And the reason it's called a critical frequency is that in the pole zero plot, it only has one pole, and it's on the real negative axis. That's negative sigma per the last lecture. So anything other than that is going to have two poles, and if the Q is less than 0.5, the two poles are going to be on a negative real axis, and if they're greater than 2.5, then they're going to be complex conjugates and have a component in the plus and minus j omega axis, and that'll give us some different characteristics not only for our frequency response but for our phase response also. So if we have a Q 0.5, the response would look something like this. The actual critical frequency, which is defined by F sub 0, is found to be about 6 dB down. It ultimately achieves a negative 40 dB per decade. Now if we adjust the values a little bit and pump the Q up to 0.707, is what we see is a maximally flat, and this is standard with Q707, maximally flat out to the corner frequency, which is 15K. Then it goes into a roll-off of negative 40 dB per decade. Now this configuration is so popular it has a name, and the name is Butterworth. So different Qs, as we'll see later, are assigned different names. For example, a Bessel function doesn't have quite the flatness of this, but it has a very, very nice phase response, and it's called group delay, where the high frequency components of the signal are delayed about the same as the low frequency components, and in certain applications that's very important. And a Chevy Chev has feedback such that you have little ripples in the passband, and that's the cost of it, but when you get to the corner frequency, it immediately dives into a negative 40 dB per decade roll-off. and that filter would have a higher Q than this circuit. So the whole point of this is the Q, as seen before in LRC, controls a lot having to do with the response and overshoots, ringing, and so forth. So if we want to change the Q on this, there's two ways we can do it, and one is changing the ratio of C1 and C2, it's what we're going to do, and the other one is adding gain into the amplifier, and as you can see by the, see if I have this written down there, the feedback path, if I have gain in here, going to be increasing the signal coming back to this point. Now, how do we add gain? That's simple. We put RF, a resistor here, an RI resistor here, and then the equation for this now becomes 1 plus RF divided by RI, just like what we've been seeing in the past with operational amplifiers. So, C2 and C1, we're going to let these remain constant here, and as said before, this is the Q of a Butterworth at 0.707 industry standard. Now, let's see what we have to do to get the Q from 0.5, the critically damped frequency, up to that of 0.707. Now the equation which was developed before had this Q is equal to 0.5 times the square root of C1 over C2. It's another thing you have to be careful of, that you don't switch around those subscripts. And just setting the Q equal to 0.707 gives us this equation. Dividing both sides by 0.5 or multiplying both sides by Q gives us 1.414 equals the square root of C1 over C2. And then setting some things equal here, C2 is equal to 1 divided by 1.414 times C, and C2 comes out to be 7.07 nanofarads. That's this guy here. So he dropped in value. And likewise, C1, if we calculate him, is being 1.414 times C. We end up with this as being 14.14 nanofarads, which, as you can see, is going to increase the feedback to this point. Now, what the books say about this is we're multiplying and dividing by a number that they call M and N. And in this case, I haven't gone through that step to introduce another variable. I'm just using the raw term 1.414 and its reciprocal 0.707 to get this guy. But do note, if you multiply C1 and C2 together, you're going to end up with 10 nanofarads, and that's important. So this is the overall diagram of the thing with our 7.07 nanofarads and our 14.14 nanofarads. So if we take a look at the real and imaginary impedances, we notice that they have the same ratio as the LRC. The magnitude can be different, and what we can see here is a pole zero plot. Here I have negative sigma, positive sigma, and we always have to be in the right hand plane if we're dealing with filters. Locating a pole on the J omega axis leads to instability, severe instability. And if we're over here, we either have an oscillatory issue in quadrant 1 or a growing exponential issue in quadrant 4, undesirable for our purposes. So what we've done here to find the poles here, and I've just written these down as x's, 45 degrees between the two of these, and this is what they come out to be as negative J 660, 66.6K, negative 66.6K, and a positive J 66.6K. So any X on the connecting hypotenuse there will give a Butterworth response. So let's see if we can find the poles in Sallen key, and what we do is we set the denominator equal to 0. Setting the numerator equal to 0 will find us our 0 points, the points of zero transmission. Now, in a low-pass filter, that zero transmission is at infinity. So that's something we can't really plot. In a high-pass filter, the 0 is at the origin. It's not going to pass 0 hertz. It's a high-pass filter. So the numerator deals with the zeros and the denominator deals with the poles. So all we have to work with is the denominator here, and here's our guy right here. Now, substituting this into the quadratic equation, what I do is, so I don't end up with a calculator entry that long and make a mistake and have to go do it again, is I break this down into subparts, and I usually do it in Excel because it's easy to fix and it propagates change directly through so you can see answers. So I'm not interested in the omega in the numerator here, the omega squared in the numerator. I'm very interested in the second order equation in the denominator. So in this, I'm going to let a equals 1, and b is going to be equal to omega 0 over q. That's this guy. And a is 1 would be the coefficient of s squared, which is 1. And finally, c is going to be omega 0 squared. So once I have that, not too hard to follow. So here's our setup here, setting them equal to 0, and omega 0, using 15 kilohertz as our corner frequency, comes out to be 94.282 k rads per second, and omega 0 squared is 8.88 e to the 9th. Now the reason I'm doing this up here is I'm going to need them later, so I'm figuring them out of the way. Q is equal to 7.07. So we're starting out with our equation here. Important to remember this is negative b. A equals 1 as said before. B equals omega over q. And doing the calculations on that now, we're dividing our 94.282 rads per second by 0.707, which gives us 133.3 K. So the real part of this we can solve right now. All we have to do is take this value and divide it by 2, realizing that this would be that's a negative sign here. Let me make him a little darker. There we go. And the real part of this is going to be negative 66.65 K. So we found one of the roots very quickly, and all we had to do is use b to solve it. And that would be this guy right here. Now the solve for the imaginaries is a little bit more involved in what we're dealing with, and I've just segregated out the radical here divided by 2. And now I've substituted in my values here for b squared and minus 4 times, I'm sorry, yeah, b squared minus 4 times omega squared, correct, 4 times omega squared. We have to divide it by 2, and what that gives us is 17.72 e to the negative 9 minus 35.52, let me say that again, 17.77 e to the 9th power minus 35.52 e to the 9th power. And that gives us here plus or minus the square root of negative 17.75 e to the 9, again divided by 2. Well, we immediately pick up a problem here, taking the square root of a negative number. Kind of hard to do that. So what we'll do is we'll extract the plus or minus j out here and treat the radicand as a positive number. And in so doing, this gives me 133.3 e to the 3rd divided by 2. Gives plus or minus j 66.6 K. And that are these guys right here. So we just dot the lines, put the x's in, we got our poles. Now if you draw this in multi-sim, it'll give you the poles also. You have to analyze analysis and then go down the pole plot, but it's restricted in range from the critical frequency 0.5 up to about q equals 2. It won't give you answers outside of that range, which is kind of unfortunate. So here's the whole deal here. Nice and clean. We have our poles, and if you go back into the first lecture video on this, is you'll see the 3-dimensional rendering of a pole zero plot And that, I think, adds a lot of insight into what we're actually looking at. I'm not going to do that again here. So the second option is adding gain, and I've included two resistors here. Now these are all equal valued parts again, and depending upon the gain I can get different responses. As mentioned before, Butterworth is maximally flat, and if you look at that handout, what you'll see is on transient response, hitting it with a square wave, it's got a little dimple at the top. So that's the cost of getting something that's maximally flat. Now Bessel won't give you that. However, it's not maximally flat. So if you're dealing with group delay issues, and remember that a square wave or a rectangular wave is made up of high frequencies on the rising and falling edges and low frequencies on the tops and bottoms, is a square wave or rectangular wave that comes through looking that way means that you got good phase response. If it's not rounded, which would attenuate the high frequencies, they're not overemphasized, which would accentuate the high frequencies. So we have these standard gains, and this is all set up by the industry, and these are common names for common filter responses. And then the question is well, how do I end up with a gain of 1.586 if I want to build a Butterworth? Here are values again. So all we do is fall back and take a look at the gain for a non-inverting amplifier. AV equals 1 plus the ratio of RF over RI, and then we substitute in 1.586 for the gain we want. Subtracting 1 from both sides is what we find is the ratio of RF over RI is equal to 0.586. Okay? So again, we're going to let one of them be something so we can figure out what the other is. And in this case, I let RI equal 10K and RF 5.86K. And when you put that back into the gain equation, it's 1 plus 5.6K over 10K, which gives us our gain of 1.586K. Now this is a little bit unusual because RF is smaller than RI, and that puts us in a gain range of between 1 and 2. So that'll conclude with active filters, and thank you for watching.